Welcome to another Intermediate Algebra video. In this video, we will look at solving radical equations. So we've done a lot of work with radicals, a lot of simplifying, add, subtract, multiply, rationalize, and now we're going to actually look at being able to solve an equation that contains radical expressions, and then one application of that, which is the Pythagorean Theorem. So the notes for this section. The first set of notes is the set of steps on what to do in order to solve an equation that contains a radical. And it might have one, it might have two. I suppose more than two is possible, but not something I would expect you to see. So what's important and new about solving a problem like this is that when you solve, you do need to go back and check your solutions. A lot of textbooks and math classes will show you how you can check a problem once you've completed it, but it's always kind of an optional thing. But when it comes to radicals, you need to check it in order to make sure that that solution is a good solution, or solutions are good solutions. And you'll see why when we go through some problems. So these are some steps we can follow to solve problems. The first one would be isolating one of the radicals. If there's only one, then that's the only thing you'll do, isolate the radical. Then we'll raise each side to the power equal to the index and simplify. So if we have a square root, then we're going to square it, both sides of the equation, because the second power will undo the square root. Then the third step, if a radical still remains, repeat steps 1 and 2. If not, continue solving. And then the last step would be to check all proposed solutions. There might only be one, there might be two, just depends. And then the Pythagorean Theorem is kind of an application that'll involve solving with a square root. It's for a right triangle. As you can see, a right triangle. We know it's a right triangle when we see this little square in the bottom corner, or any corner of the triangle. And the most important piece to that triangle is the C. This piece is the hypotenuse. And what you should note is that it is by itself in the formula. The A and the B are interchangeable. If you labeled this left side B and the bottom A, your formula would still work out the same. These two would just be flip-flopped. But it's very important to have the C on its own by itself. All right, so let's start to look at some problems. All right, the first set of problems we're going to solve. So as with any problem where we're asked to solve, we are looking for the value or values that would make this a true statement. So the first one, the square root of 7x is equal to 7. So the first thing we want to do is isolate one of the radicals. We only have one radical here, and nothing else is happening to it. There's no addition on the end, there's no multiplication on the outside, there's no division underneath the whole thing. So it is isolated. We can go right into step 2, which is raise each side to the power equal to the index. Remember, if we don't see an index, we don't see one explicitly written, then the index is a 2, which means we want to square each side. So when we square each side, on the left, the square root and the square undo each other. We get 7x. On the right, 7 squared means 7 times 7, which is 49. The third step would be repeat 1 and 2 if another radical remains, but we don't have one, so we will continue solving. And that just means whatever process might be left. So we want just x, so the only way we can get that is by undoing this multiplication. Divide both sides by 7, we get x equals 7. Okay, so we have one proposed solution. Let's go ahead and check that. Our last step, we need to make sure that this gives us actually a true statement. So we'll plug in, instead of x, we'll plug in the 7 that we just found, and we want to see if this is a true statement. So on the left, square root of 7 times 7 is 49, and then the square root of 49 is 7, which is a true statement. So that means our proposed solution is a good one. Okay, the next one. The square root of 2x is equal to -3. So first step would be to isolate the radical. There's only one of them, so this is the one we'll focus on. And it's already isolated because there's nothing else happening to it. So we can go ahead right away and raise each side to the power equal to the index. Again, the index is a 2 since we have a square root. So on the left, the square root and the square undo each other. We get 2x. On the right, -3 times -3 is +9. Step 3 says if there's a radical, start over, isolate and get rid of it. If not, continue solving. So we'll divide both sides by 2. We get x equals 9/2, or in this case, a decimal would be okay, but the 9/2 is more preferable. All right, we have one proposed solution. Let's see if it's a good one. So back to the very beginning, 2 times 9/2, and we need that to be equal to -3. 2 times 9/2 will give us 9 underneath that radical, and then the square root of 9 is 3. So we get the statement 3 equals -3. That's a false statement, which means this proposed solution is not a good one. If we don't have another one to check, then that's it. There is no solution. And that's why it's important to check on these problems. Now, for this one, we could go back to the very beginning and we could figure out right away that there wasn't going to be a solution. In this one we could, but it's not always that simple. So if you go back to the original problem, square root of 2x equals -3, we're looking for something to plug in for x that we can multiply to and then ultimately take the square root of and get a negative outcome. Will we ever take the square root of something and get a negative outcome? Not unless there was already a negative on the outside, and there's not. So for this one, you can see at this point, because there's a negative on the outside here, it's not going to work. And more specifically, the reason it won't work is because it's a square root. If we had a cube root and we were looking for something that was a group of 3 to come out of that radical, well, then that's possible. You could get a negative, but it's a square root, so it won't work. Any even index would give you that type of problem. Again, easy to make that call on this one, but as we continue on, sometimes there might be a variable remaining on the right-hand side, and if that's the case, even if it's negative, you can't say whether it's by default going to be no solution or not. You just have to see how the numbers play out. All right, so let's do another one. So the next one, the square root of 3x minus 5 minus 4 equals 0. The first thing is to isolate one of the radicals. There's only one, so we isolate it by adding 4 to each side. We get the square root of 3x minus 5 equals 4. Now you might be wondering, why couldn't I square this quantity right away to undo that square root? If I took, the square root of 3x minus 5 minus 4 and squared that whole thing, that would mean that we were squaring the whole quantity. So you'd have to go through the whole process of FOIL, which you can do, but it's ultimately not going to get rid of the radical. It'll get rid of the first one, but then your two middle terms will still have a radical, and you'll have to start all over again. So it's very important that you don't square each side until at least one of the radicals is isolated. Okay, so we've isolated on our problem. Now we can raise each side to the power equal to the index, which is a 2. Let's bring this up here. On the left, the square root and the second power undo each other. We get 3x minus 5. On the right, 4 squared is 16. Continue solving. Add 5 to both sides. And then divide by 3. We get 7. 7 is a proposed solution. So let's go back and check to see if it actually works. Our initial problem is the square root of 3 times 7 instead of x minus 5 minus 4 equals 0. So we want all of this to boil down to 0. So on the left, we get 21 minus 5. Then we get the square root of 16, which is 4. We get 0 equals 0, which is a true statement, which means x equals 7 is a good solution. All right, last example on this page. In this one, we have the cube root of 2x is equal to 4. So the first thing is to isolate the radical. It's isolated, nothing's happening to it. The second step is to raise each side to a power equal to the index. In this case, the index is a 3, so we need to cube each side. On the left, cube root and the third power undo each other. On the right, 4 to the third power, 4 times 4 is 16, times another 4 is 64. Then, if there's a radical remaining, start over. If not, continue solving. We'll divide both sides by 2, and we get x is equal to 32. That's our proposed solution. So again, the very last thing we do is check. So back to our initial problem, 2 times 32, and we want that to be equal to 4. Now, for a problem like this, there's no addition subtraction happening underneath, so you could multiply 2 times 32, get 64, and then take 64 and break it down. Or you could just kind of start with some of the pieces broke down, take that 32 and break it down. 32 is 16 times 2, 16, 4 times 4, 4, 2 times 2. So underneath we have the 2 that already existed, and then 5 more from the 32. And we want that to be equal to 4. Running out of space. Okay, remember this is a cube root, so we want groups of 3. We have 2 groups of 3, each containing a 2. So a 2 comes out and a 2 comes out, nothing's left inside. We get 4 equals 4, which is a true statement. So x equals 32 is a good solution. I know it's tempting to look at these and say, let's just assume every time that it works, but as we continue on, you'll see it varies and it becomes more difficult to check. Maybe not more difficult, but the number part, it's a little fuzzier as you go through, not quite as simple as looking at this and saying, yeah, that's exactly, we didn't do a whole lot of steps to solve, so there's not a whole lot of steps to check. But checking is part of the process on these problems to make sure that you have the right thing. All right, so let's continue on with some examples here. The next one, the square root of negative 10x minus 1 plus 3x equals 0. First thing is to isolate the radical. So the radical, and then on that side we have a plus 3x. So let's subtract 3x to isolate it. Then, once it is isolated, raise each side to the power equal to the index. That index is a 2, so we'll raise each side to the second power. On the left, we get 10x minus 1. On the right, remember this means negative 3x times negative 3x, which gives us positive 9x squared. And I know it's tempting to look at that second line that we had and say, well, no solution is going to work because there's a negative on that side, but we don't know what x is. If x is negative, it'll multiply by negative and become positive, which would be okay. So we continue on. We'll go back and check when we get to our final solutions. So we have 10x minus 1 equals 9x squared. Okay, the goal, because there's not a radical, so step 3 says if there's a radical remaining, do it again until you get rid of all the radicals, but there's not. So all we're left to do now is continue solving. Now, if we have a second power involved in the problem, it takes a specific type of solving, different than the problems we've seen thus far. Those were all linear, and so they would only potentially get one solution, but since there's a second power involved, potentially we get two solutions. And so the only method we have thus far to solve this problem is factoring. Now, remember that in order to use factoring as a method for solving, it needs to be equal to 0 on one side or the other. So we have to bring all the terms over to one side. I'm going to choose to subtract the 10x and then also add 1. And the reason I went and got everything to be on the right side is that my x squared term was already positive. And in order to factor, it's preferable to have that first term, the x squared term, be a positive. So if you went the other way, you just have to fix there being a negative. All right. So here is our problem as it stands. And we've already looked at methods for factoring, so you can use whatever method you would want to get to the fully factored part of this problem, but I'm just going to go ahead and factor it for us. We've already seen this. You can go back and review on factoring if you want to. We get 9x plus 1 and, x, what am I missing? This was positive. Oh, here we go. There was a negative here, so this was a negative. So we add it to both sides, which makes this a plus 10, and then they're both plus. Sorry about that. So here are the two factors, 9x plus 1 and x plus 1. And then remember, once you have it factored, you know that if these two things are going to multiply and give you 0, one of those two things has to be 0. So it's either that 9x plus 1 is equal to 0, or that x plus 1 is equal to 0. And then you solve these two. I like to call them mini equations. Subtract 1 from both sides, divide by 9, we get x is equal to 1/9. And for the other one, subtract 1, we get x is equal to -1. But then, don't forget, the last step of solving an equation that contains radicals is to ultimately go back and verify your solutions. So, now we have 2 to check. Let's start with the -1. You can probably fit this in a small space. So we're plugging in -1 for x. So here's what we're trying to verify. The square root of -10 times -1 minus 1 plus 3 times -1 equal to 0. Underneath, we get positive 10 minus 1. This becomes minus 3. Square root of 9 minus 3. 3 minus 3. 0 equals 0. True statement, which means this x equals -1 is a good solution. The first, or I suppose the second of our solutions, was a good one. All right, let's also check our second, or our other solution. The square root of -10 times -1/9 minus 1 plus 3 times -1/9 equals 0. So underneath this radical, we get 10/9 minus 1 and then minus 3/9. Underneath the radical, we'll change that 1 to be a 9/9 instead, so they're common denominators. The 3/9 will simplify to 1/3. When we subtract underneath, we get the square root of 1/9. The square root of 1/9, remember, if you can take the square root of the top and bottom, you can do it at the same time. We have 1/3 minus 1/3 equals 0. 0 equals 0, which is a true statement. So in this case, both solutions were good. It's very possible for one of the two solutions to work or neither of the two solutions to work. There's no easy way to tell. You just have to go back and check by plugging them in. One more with me. Okay, so now a problem that involves two different radicals. So the first step is to isolate one of the two radicals and then raise each side to the power equal to the index and continue on from there. All right, so it's really your choice which one you want to isolate. You'll come up with the same answer or answers either way. You just have to make a decision. So let's go with isolating the square root of 2x plus 5. If this is the one we decide to isolate, then we get rid of the other term. Whoops. Change that back. So we subtract the square root of 2x from each side. We have 2x plus 5 under the radical equals the 3 and the minus 2x. They don't combine in any way, minus root 2x. Okay, so we've isolated one of them. Now we can square both sides. The left is the easy side, square root, square, undo each other. That's all that's happening over there. But on the right, we have a quantity. We have a term and another term. This is what this quantity squared means. 3 minus square root of 2x times the quantity 3 minus square root of 2x. So I'm going to work this part out on its own and then bring it back into the problem. In order for us to multiply this, we're going to have to go through the process of FOIL. So first multiply the 3 by everything in that second parentheses. We get 9 minus 3 square root of 2x. Then distribute the negative root 2x, which gives us minus 3 square root of 2x and plus square root of 4x squared. Now keep simplifying. Those middle two terms can do something. They are alike, so they can combine to be minus 6 square root of 2x. And then the last term, the square root of 4x squared, can simplify to 2x. All right, so let's pull that back into our problem. Okay, so we've completed step 2. We raised each side to the second power. Now we're in step 3. If another radical remains, start over. Isolate that one radical and square both sides. So that is now our goal. We still have a radical in the picture. We can't do any solving until we get rid of it. We get rid of it by squaring it, but we can't square it until it's isolated. So start moving some terms to the other side. We can start by subtracting 2x. Good news, the x term is gone then. Then subtract 9, which gives us negative 4. We still want that entire radical isolated. The negative 6 multiplying by it needs to be gone. So we divide both sides by negative 6, which gives us, let's write another line. Positive 4 over 6 is equal to root 2x. But we can simplify that. 2/3 equals root 2x. So again, we've isolated. We're back to step 2, which says raise each side to the power equal to the index. On the left, we get 4 over 9. On the right, square root, square, undo each other, we get 2x. Then we're back in step 3. If a radical remains, start over. Well, we no longer have a radical, so we continue on. If not, solve. We divide both sides by 2 with a little keep, change, flip. We get 4 over 18, which is 2 over 9. Oof, getting ahead of myself. So we get 2 over 9, which is our proposed solution. So we go back to the very beginning to check. And it's not nearly as much work to check it as it was to solve in this case. So Let's see what happens when we verify this solution. We have 2 times 2/9 plus 5 plus 2 in the radical times 2/9 equals 3. So under that first radical, we get 4 square root of 9 plus 5. 4 square root of 9 equals 3. You can use the calculator to do a little bit of work on these. You can get decimal approximations. You can type in under the radical. If we type in the 4/9 and add 5 to it, then change it back to a fraction, we get 49/9. Then each one of these you can take the square root of. We get 7/3 plus 2/3, which combines to be 9/3. And 9/3 is 3, which is a true statement, so yes, 2/9 is a good solution. All right, so we saw kind of a buildup of a lot of different types of problems, equations that involved radical expressions. All right, I think, okay. We'll go through the Pythagorean problem and then we'll get to practice. So Pythagorean is just an application of an equation that may involve solving with a radical. If you can't see the pieces, this left-hand side is a 3, the bottom is a 4, and the long piece is a C. All right, so we have 2 problems. The first one gives us a picture, the second a word problem. These are separate. I think I'll need some space. So the first one asks us to just find C using the Pythagorean theorem. Well, it doesn't say to use it, but that's your option if you have a right triangle. And you have 2 sides and you're solving for a third. So let's remind ourselves Pythagorean theorem is a squared plus b squared equals c squared. So in this case we have a and b. You can call 3 and 4 a or b. And then c, the side by itself. The longest side is the one by itself. So if we plug these in to solve, we have 3 squared plus 4 squared equals c squared. Each side length is squared when plugged into the formula. So we get 9 plus 16 equals c squared. 25 equals c squared. And we haven't seen a problem where we had to solve this way yet, because one method we have is to factor if we have that second power involved. But if it's as basic as this one, using Pythagorean theorem, you can undo that second power by taking the square root of each side, which gives us c equals 5. Square root of 25 is 5. So this missing side is 5. So again, plug everything into the formula and then solve. Okay, our second problem, a 13-foot ladder is leaning on a 12-foot tall building. Let's add the word tall in there. How far from the building is the ladder? So let's get a picture of what this looks like. There's a building. Down with windows, sure. And it's 12 feet tall. Okay, the other thing we know is that there's a 13-foot ladder leaning against this building. So here's a ladder. And the question, how far from the building is the ladder? So this is the length we're looking for. Now, it doesn't say it explicitly, but you can assume that when a building hits the ground, it creates a right angle. You can make that assumption, at this level at least. And so this is the problem we're solving. Well, since it's a right triangle, that means Pythagorean theorem will be helpful, can be helpful. So let's plug in the pieces. The formula, a squared plus b squared equals c squared. The most important piece is that longest side, in this case, which is the 13. Then the other two sides, it doesn't really matter how you fill them in. 12 squared plus, instead of b, x squared, and this is what we're solving. 12 squared, 144, 13 squared, 169. Subtract 144 from each side. When we subtract, we get 25. Continue solving for x. Take the square root of each side, we get x equals 5. You can expect to be able to solve any Pythagorean problem using the square root at this level at least. So ultimately, since this one did talk about units of length, we should write in a unit. This was 5 feet because everything else was in feet. So the base of the ladder, 5 feet away from the building. Good. All right, let's do a little practice. Okay, one solving problem and one problem that uses the Pythagorean theorem. Go ahead and pause the video and we'll go through this together in a quick moment. All right, so you've attempted these problems. Let's see if you got them right. So the first problem, we're solving for x. We're looking for the value that would make this a true statement. First step, isolate the radical. There's only one here, so we will isolate the one and only radical. Add 7 to both sides. Square root of 3x minus 5 equals 7. Then raise each side to the power equal to the index, which is a 2. So on the left, we get 3x minus 5. On the right, 49. 7 squared, 49. And then continue solving. There's no radical left, so we can solve as usual. Add 5 to both sides. We get 54. Divide both sides by 3. And we get x equals 18. This is our proposed solution, so hopefully you made sure to check this. Back into the initial equation. We plug in 18 instead of x and then verify. 3 times 18, 54. 54 minus 5, 49. Square root of 49 is 7. Negative 7 plus 7, 0. True statement. So x is 18 is a good solution. Hooray. Good. Okay, the second problem, a Pythagorean theorem problem. This will use a squared plus b squared equals c squared. The most important piece to fill into the formula is the c. Oh, we don't need a there. Which is the 21. So we'll say x for a, x squared plus 15 squared equals 21 squared. And then this is what we're solving. X squared plus 15 squared is 225. And 21 squared, 441. Continue solving. Subtract 225 from each side. We get x squared equals 216. Then take the square root of each side. I'm not sure it's a perfect square. Let's see. Nope, it's not a perfect square, so we'll have to simplify. We'll take 216 and start breaking it down. We need to see if there are any pairs in there. We can definitely start with a 2. Oh, whoops, not a 4. 2 and 108. This 108 can go to 2 and 54. 54, 9 and 6. 9, 3 and 3, 6, 2 and 3. So it looks like a pair of 3s and a pair of 2s. So a 2 times 3 comes out and a 2 times 3 is left inside, giving us ultimately 6 root 6. The expectation on any radical problem, if it's not a perfect square, is always to simplify in the end. And so this would be your simplified answer. The good news with the Pythagorean Theorem problems, you don't need to go back and verify. You can if you want to, but it's not necessary. Where the problems that we actually solve an equation where we're not exactly sure what it is we're referring to, we need to make sure that they give us, that the process we use gives us a viable solution. All right, so in this video, we looked a little bit at the Pythagorean Theorem, one application model of this type of problem, and then at a whole bunch of equations that involved a radical expression. I'll see you soon for another video.